All right. Good morning, everyone. It's good to see a packed house. Thanks for coming so early in the morning. This is the first of the Khronos Developer Day sessions. And this is a session where we're going to be talking about the standards and technologies that Khronos are developing that are relevant to bringing gaming to the web. My name is Neil Trevitt. I work for NVIDIA. It's my day job. I'm the president of the Khronos Group, and also I'm gITF chair. But luckily, we have lots of good speakers that are going to give us lots of interesting details around WebGL, gLTF. But before we do that, we wanted to spend just a couple of minutes talking about some of the other initiatives that Khronos have been launching here at GDC and show how they too are potentially relevant to the web as well. And then we'll start diving down into some details. These are the 5 things that Khronos have been talking about here at the show. We're going to be talking about WebGL 2. We're going to be talking about gLTF 2.0 as well. But some of you might have seen OpenXR. This is the new standard for cross-platform portable virtual reality. And we've also done a call for participation for our newest exploratory group, which is a Portability API. So let me just spend 20 seconds on each and come and talk to us afterwards. And there's some of the sessions later in the day we'll talk in more detail about these. OpenXR VR is awesome, but it's very fragmented. Applications have to port to lots of different SDKs. It's hard for the new devices to integrate into SDKs and be accessible by applications. OpenXR is an emerging standard that defines 2 APIs, an application-facing API set, so you can write an application once to run everywhere across all of the key VR runtimes, but also a device layer that lets people innovating, interesting tracking and other display devices to self-integrate their devices so they become accessible to applications in the ecosystem. We've just started. This is a new initiative. We have a bunch of good working group members, so it's kind of a who's who of the VR industry. Today, or actually I think it was yesterday, Mozilla came onto the working group, so that's cool because it kind of shows that it is relevant to the web. We have just started. These things normally take around 12 to 18 months, so you know, something at GDC would be a stretch goal, but we'll see what we can do. The reason I'm bringing it up here in the web session is it is relevant potentially to WebVR. WebVR is using WebGL for rendering, and OpenXR does not replace WebGL. It's not another rendering engine. It's taking care of all the stuff that's not rendering, all the sensor, pose estimation, getting to figure out what devices are in your VR system. So we're hoping that the defragmentation of OpenXR at the native level can help WebVR be more portable more quickly to more VR systems. So watch this space to see how that works out over time. The other new thing, which is really, really new, the Khronos board just decided this on Friday, is something we're calling a 3D Portability API. We've been approached by a lot of native developers saying, we have a problem, we want to run the same code across systems that have Vulkan, Metal, and DX12, but there's no real standard solution to do that. Can you help? So we're starting that discussion to figure out whether we can help, perhaps, and everything here is, discussion hasn't even really started yet, but this is kind of the targets that we're going for. Can we perhaps do a intersection of the 3 APIs, come up with a usable API surface that we can specify and ratify so people can write to that API surface with some confidence, and that code can be translated to run on any of the underlying systems at pretty good efficiency. Of course, it's not just the APIs, you have to figure out the shading languages, but there's an increasing amount of open source from Microsoft, from Khronos, around SpearV and other intermediate languages. Perhaps we're kind of converging, and with enough open source, we can give shading language flexibility. Bringing those 2 things up might produce a portability solution that might be useful to the industry at the native level. And that in turn might well be possibly useful to WebGL Next. And we've just started the working group for WebGL Next discussions. And again, no decisions, but there's very interesting, potentially synergistic discussions ongoing between what does web need, what does native need, and can we perhaps share some work and share design, get there faster and better. So if you're interested in any of that stuff, which is all kind of the things that are coming down the pipeline, please do come talk to us. We'd be delighted to talk to you. So that's enough for me for now. We have these awesome speakers. We have Google going to be talking about WebGL 2. We're privileged to have Mr. Doob here, 3JS. Brandon from Google going to be talking about WebVR, myself, and Saurabh from Microsoft talking about gITF, and then we'll hopefully have time for some Q&A. So without further ado, WebGL 2.
Thanks, Neil. All right, so hi, I'm Kai Ninomiya. I'm here with my colleagues Senyam Mo and Ken Russell. We work on WebGL on Chrome, and we're here to talk about WebGL 2. So first, a little bit of background on WebGL. WebGL is being used for all kinds of 3D visualization and presentation on the web today. It's all over the place. We've got artists using it to show off their work. The New York Times is delivering content to their users with WebGL. So it's all over the place right now. And here's why WebGL is useful in games, right? Everyone has a web browser. And WebGL just works for pretty much everyone. According to some various stats, we have 90 to 95, 96% of all web browsers, of all users on will have this in their web browser by default without having to do any extra work. So this is really powerful, right? This means you can deliver a game to your user without them having to download anything or install anything. All they have to do is end up on your web page, and there's the game. There are a number of game engines targeting the web right now. So of course, Unity has its HTML5 target, which uses WebGL. And there are a number of open source, pure web 3D and game engines, like PlayCanvas, Turbulence, Babylon.js, 3JS. So there's a lot of support in this area. Here's a little screenshot. This is a really low resolution screenshot of WebGL 2 and WebVR being used together. This is a particle simulation with 500,000 particles running in a web browser, and this works on mobile devices. It works on desktop devices with Vive, as you can see in the image, and so on. I'm just going to show a little bit of this demo from PlayCanvas. So this is their WebGL 2 launch tech demo. So this is running, of course, live in my browser right now. This is not a video. This is actually WebGL 2. So this is showing off all sorts of really cool features and things that can be done with WebGL 2. They have the procedural clouds that you can see in the background, procedural water ripples and reflection, leaf particles, the animated trees blowing in the wind, mirrors, dynamic lights, compressed textures for reducing the size of the assets, asset streaming, runtime light map baking, and lots of other stuff. So there's a lot of really, really cool stuff going on here, and it's all running on top of WebGL 2. And so anybody with a browser with WebGL 2 will be able to use this demo. I have it on low quality because this is a MacBook Air, and it's very GPU intensive, but it's a really cool demo. So now I'm going to go over some of the features that are now available in WebGL 2. So this is sort of a spec overview, the new entry points in the API. So WebGL 2 exposes the OpenGL ES 3.0 feature set. So formerly, WebGL 1 was exposing OpenGL ES 2.0. With WebGL 2, we're now exposing OpenGL ES 3.0. And this really brings desktop and mobile platforms feature sets a lot closer together because OpenGL ES 3.0 adds a lot of features that were formerly only available on desktop platforms that are now available available pretty much everywhere. So we've got a bunch of features that I'm not going to talk about right now because I'm going to go into a little bit more detail on them. So WebGL 2 is here now. WebGL 2 is available in Chrome and Firefox. In Chrome, it's released on desktop platforms. Soon on Android, Firefox is released on all platforms. Edge and Safari also plan to ship WebGL 2. Desktop support is already at 35%. This just came out in January, and will continue rising as we get more and more support and as we support more and more devices. WebGL 2 is, we think, very reliable. It has a huge test suite. We're passing 100% of this test suite on Chrome, and Firefox is passing very nearly 100%, so it should be a very, very robust. You should not run into too many bugs using WebGL 2. So that's a great, makes it a lot easier to get into it. So a few of the features that we now have. We have more texture formats, floating point textures, unsigned and signed integer textures, which means you can do a lot of computations that formerly would lose precision when saving into a texture. We have sRGB formats for higher quality rendering in linear color space. We have ETC2 and EAC compressed textures via an extension, which will be available on mobile platforms, and other compressed texture formats available on other platforms. We have 3D textures and 2D texture arrays, great for volumetric effects, medical imagery, all sorts of good stuff that you can do with this. The volumetric clouds that you saw in the last, in the Play Canvas demo. By the way, I forgot to say, all of these links, obviously you can't click them. All of these links are in the presentation. We have not published the presentation, but we will. So don't worry about scrambling to take down notes or anything about all this stuff, you know, because I'm not talking about most of the material on these slides. So please, we will send out the link, and you will be able to. We'll publish the link, and you'll be able to go through these slides on your own. Right. So we have immutable textures, which give us great performance improvements on a lot of platforms, especially on Windows when we're implementing WebGL on top of Direct3D. Full support for non-power of 2 textures, seamless cube maps. And this is a great feature, instancing. So in WebGL 1, if we wanted to draw 1,000 things, 1,000 soldiers, that would require 1,000 draw calls plus 1,000 different uniform sets and so on. So that was a huge amount of CPU time just to get that on the screen. Now with WebGL 2, you can do all of that with just one instance draw call or with just a few, and you get a huge performance improvement by doing this. So there are a number of demos here that you should check out, but the performance improvement by using instancing is really great. We have multiple render targets, so this allows you to render to multiple frame buffers in one pass. So the fragment shader can now output multiple values. This was, of course, has been available as an extension and was available on desktop platforms for a long time, but this is very powerful technique for deferred shading and lots of other techniques on the web. We have integer vertex attributes, so now we have pretty much full integer support in WebGL 2, so it goes hand in hand with transform feedback, integer texture support, and there's lots of good things that you can do with integers on the GPU. Transform feedback, you can save the output of the vertex shader directly into vertex buffer object. So that means you can cache and reuse GPU computation. The crowd demo also uses this for doing the skinning just once for each variant of the model, and then rendering all of the soldiers without reskinning each of them individually, which also saves a lot of rendering time. Stateful particle systems like the interactive particle demo that we saw with WebGL 2 and WebVR. And they're also, in the Play Canvas demo, they're also using this for a couple of things like the simulation of the leaves. So a lot of good particle effects are out there. We have multi-sampled render buffers, so this allows you to do efficient anti-aliased off-screen rendering. There are all sorts of useful things that you can do with this. You can get higher quality rendering for deferred shading and so on. Vector curve rendering can be implemented with this, so a lot of good techniques there. We have a bunch of new GPU-side copy and compute operations. So a lot of, in WebGL 1, often if you wanted to do a lot of operations, it would involve a lot of bringing stuff back to the CPU, doing something there, bringing it back to the GPU. So there's a lot of stuff now that we can do without doing that extra copy. We have copies between textures and pixel buffer objects. We have transform feedback. We can render to 2D texture arrays and 3D textures, which make a lot of volume rendering algorithms now possible, and fluid simulations and all sorts of great stuff. features for performance optimizations like uniform buffers. This actually gives a huge speed up if you're uploading a lot of uniforms at once, which is very common in a lot of applications. So now we can upload many uniforms in a batch with one API call, which saves a lot of time. Vertex array objects and occlusion queries, which are great for a lot of optimizations. We have sampler objects, so now now the sampling parameters and the texture can be separated inside of the outside of the shader, so that they can be combined inside of the shader, which allows like much easier usage of shaders of textures with different types of sampling parameters inside of shaders. And of course, we have all of the features of GLSL ES 3.00, such as texture lookup in vertex shaders, centroid interpolation, fragment discard, flat and smooth interpolators, non-square matrices, and sampling textures by level of detail, and lots of other things. Everything that's available in GLSL ES 3.00. And there's a bunch of other stuff that I didn't list here, and many new effects that nobody has implemented yet in WebGL 2. But pretty much anything that's possible with WebGL or with OpenGL ES 3.0, we can now bring to the web. And there are countless applications. I wasn't able to find a big list of them, but there's so many things that you can do with OpenGL ES 3.0 that can now be done cross-platform on any device on the web. So if you want to take a look more into the spec, there's a link here. It's easy to find on Google. So just dive in. There's a lot of stuff there. All of the WebGL 2 spec is in there. It builds on top of the WebGL 1 spec, and it also builds on top of the OpenGL ES 3.0 spec. So all of the techniques that are familiar to you in OpenGL ES 3.0, you can figure out very easily how to use those in WebGL 2 just by looking at the spec. Also check out the WebGL 2 samples pack for minimal examples of a lot of these different features, the API features. Sorry. Looking forward, in the future, we are looking at a compute shader extension, which would bring a lot of new power from OpenGL ES 3.1 into the web. So advanced effects, GPU computation, parallel data structures, algorithms, physics simulations, ray tracing, AI neural networks, all sorts of things that can be done on the GPU can now be accelerated if we add this extension. So this is something that a lot of people have been asking for a long time, and it's on our roadmap to experiment with this and see what we can bring to the web. In addition, we are looking forward to a next-generation web graphics API, as Neil alluded to. There has been, for a while, widespread interest from developers and the browsers to create a new graphics API, something that's sort of based on the design concepts of Vulkan Metal and Direct3D 12. But with all of the constraints provided by the web built into the design, so security and everything that we need in order to make things work well on the web. And we also want this to target JavaScript and WebAssembly. WebAssembly is a very important technology for games because it allows you to squeeze a lot more performance out of the CPU while still living inside of the browser. So between WebAssembly and a new next-generation web graphics API, the amount of performance over the current standards should be a huge leap. So finally, the amazing power of the graphics processor is already available to web developers on almost all of their use. Almost all of your users will be able to use WebGL already. WebGL 2 provides a lot of new features and a much-needed upgrade to the capabilities of WebGL, which will enable lots of new amazing stuff to be built and shipped to the web. So now, this is where we need you. We need you to create whatever you can with these new graphics capabilities. So please, let us know what you work on. Let's see your experiments. Let's see what you can do with these technologies. Many thanks to all of these people who have contributed to WebGL 2, the Khronos group, and many, 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 many others who have contributed to the implementations and the tests and the and demos and the community and so on. So thank you very much.
All right. Hello, everyone. I'm just going to do a quick update of more or less what happened over the last year or so. I don't think I got to do an update on last GTC, but it should be like a something that time frame. So yeah, I'm Ricardo Cabello, and I've been maintaining 3JS for about 7 years now. Now the website is 3JS, and it's basically for those of you that don't know, it's like a JavaScript library that sits on top of WebGL and aims to make also 3D a little bit easier to do. So 7 years, 84 releases, working on the 85th, hopefully for next month, and around 750 contributors. Oh, I forgot the audio actually. Is the audio working?
That? Why is it rotating so quickly?
Cool.
I don't even see that it's a
Anyway,
cube.
so sorry about that. So rather than trying to explain what it is, I'm going to show a little bit. I found a couple of funny videos that kind of show you how you start and how you end. So.
What is that? Why is it rotating so quickly? I don't even see that it's a cube.
It's what this I was following the instructions on the 3.js website. I've programmed this using 3.js.
This is from a teacher. I'm not don't remember the university, but at some point he was using a 3.js for teaching graphics to the students.
What they've done is they invented a language. Well,
this part, we can put the audio bit up.
Well, there's something I have to tell you about. 3JS is a computer language that's being developed by people who are not professionals. They're just kids who are smart, okay? The problem with them is they have no real organization. It's very difficult to work with these guys. And they just write whatever they want, do whatever they want. They're kind of loose. The problem with it is that because they're loose, they will take their system, the 3GS system, and they'll change it overnight, and some of the things you've been using won't work anymore. Okay, that is very disturbing. So what I did was, to keep that from happening, I took one of their versions from their site and I moved it into my site and locked it down. I said, we'll keep this one for, it does everything anyway. The stuff they're doing is pretty exotic. So
So you shouldn't link to the online library. You should just download it. Anyway, also wanted to feature a couple of some projects. Starting, what a better project to start with than a THS website. Also, let's see if we can open this one. Apple has been using it on some of their products, very subtly. So, for instance, in this case, this effect of mountains is using 3, then becomes the laptop. They're doing a very nice use of WebGL in this regard. Another example. This may take a little bit to load. I think it should be much faster after this. For me, it's pretty interesting to see how people are kind of evolving, or how what we're used to normal website to be, and how they're using these new technologies to see to imagine how a website will turn to be. So, for instance, this example, this will be maybe a little bit slow on my MacBook Air, but it probably is also the resolution. But this kind of looks like a normal website until you try to drag it with your mouse, and then the whole thing becomes wobbly. Wow, this is probably too slow with this for this laptop. Anyway, you should try it on your computer on lower resolution. And there's also a little bit of a tradition of a Japanese crazy website. So it's some sort of a mashup with its songs, and I think it's a website for cookies or music video, I don't know. So yeah. Also, over the last 2 years, surprisingly, something I wasn't really expecting. I was hoping that the people will, develop projects with the library, but some people also have started building like frameworks on top of 3. So a good example is A-Frame from Mozilla, which basically tries to help all the people that want to build websites in 3D and also in VR, but without having to type any JavaScript. It's very similar to VML on the time, but a little bit like more like on steroids, I guess. Oculus has also been like doing the same thing with React VR, mainly like targeting, their own platforms. But also like trying to help, basically trying to make it easy for people to do VR experiences. And then a little bit of a dev updates. A pretty impressive amount of work has done user Lowy, improving the documentation over the last year. He's like being very rigorous. Everything was missing and moving and like basically cleaning all that up and like, it's pretty humbling to see the amount of work that he has done and to like clear everything and make it easy for people to start. Something that we're still like working on is removing geometry the geometry like object or container, let's say, or structure, as a kind of reminder, like a user explanation. This is how I decided at the beginning that geometry should look like. It will be like, this is kind of the structure, like it will be a vertices with an array of objects for each vertex. I didn't have experience with OpenGL when I started doing this. And this is obviously what it kind of looks like now, which is what you expect with attributes and everything with a buffer attribute in this case, in our case, but like basically for float type arrays that goes up to the GPU directly. The problem is that in order to do the transition, there's a lot of code that relies on all the structures. So there's a lot of code inside the renderer that kind of converts from one to the other one, and it's very tricky to, even if the professor says that we break everything, like we really try hard to like not break things. Merchant 87 has, what we're doing is like doing all the geometry generators, we're doing a buffer geometries so that they output to buffer geometry. But like if you use the buffer geometry itself, it converts from one to the other one. So the code still works, but internally, first we had to like modify all those generators so they output buffer geometry. Also, we've been like doing quite a bit of work on the gLTF loader, and we had some issues with the animation system over the last 2 weeks or so. But like we're passing all the conformance tests, like we're loading all the samples. And we also started working on the gITF2 loader. We're doing the gITF2 loader basically because some of the new gITF2 spec is not like it's compatible with the previous one, but there are some things that are changing. So instead of having to have like a loader that is like, oh, is it gITF1 or gITF2? Like use this code as other code. Like we decided to do a gITF2 loader and hopefully try to encourage people to export to gITF2 directly. That way we'll end up with a much cleaner loader than not like having like a too complicated loader for both versions. Also, we have had Apple Nation is implementation of rectangular area lights. Like for both, the one on the end is basically foam material and then the standard material. That took still. This is not super fully integrated in the library. There's some things that needs to be exampled because there is some code for this effect relies on some code that is too big that it will make the library too big, even if you're not using the light. We're still like trying to figure out how to merge everything. Something kind of fun was I decided to implement, Spite implemented IQ's idea like from many years ago. Like he had an article of how to do like a global illumination in a very like stupid way, but very effective. So basically what is happening here is that for every vertex on this model we're doing a render from the normal and see what it sees, and then like, oh, I'm seeing pink, so then it must be pink. And if you do that 3 times, like you keep doing that like at least 3 times, it becomes like bounces of the light. So it becomes like pretty, it's obviously not real time, but like if you want to have like one scene that is static and you want to make it like look much better, I can see that as being like a pass that is making things looking much nicer. We're also working on instancing. It's something that's been a little bit too tricky to also implement. Hopefully we should be having for like next version, and still kind of defining the API a little bit for that. And for WebGL 2, some people try to implement, it's kind of similar thing to gITF loader and gITF loader 2, or gITF 2 loader. We're trying to consider doing like WebGL render to, if it finds WebGL 2, use WebGL 2, but I think it was gonna become too complicated also inside. So we decided to do also a new render, WebGL 2 render, and kind of started a little bit from scratch and kind of move code from one to the other one. And also while we are at it, we have a good opportunity to make it only deal with buffer geometry, so we can also remove all that stuff. Like if you're still using geometry code, the old 3JS will still work, but if you use the WebGL 2 render, then we'll put some warnings that it only works with buffer geometry, and memory will go much slower. And yeah, that's about it.
So hello everyone, I'm Brennan Jones from Google, and I have been working on Chrome for past 4.5 years or so now, previously working on WebGL, but now I'm working on WebVR full-time, and I wanted to go over a little bit of what that is and why it relates to Khronos. So WebVR, in case you haven't heard of it, it's come up a lot today, oh, thank you, is just a JavaScript API for interacting with VR hardware. So you have Daydream Phone, Gear VR, Oculus Rift, something like that. This gives you a JavaScript API for communicating to it. You're receiving the inputs events in terms of like the motion and position, and then it gives you a mechanism for providing output to it so you can actually display imagery on the thing. Oh, goodness. So it's a kind of started off as a hobby project between me and some developers at Mozilla. And at this point, it's grown into something much bigger. We have support from Google, Microsoft, Mozilla, Oculus, and Samsung. We actually have the WebVR representative from Microsoft in the audience today. And it's making good progress. We're all very excited about it. So really quick, some videos so you can see what I'm talking about. So this is me using a HTC Vive at my home, viewing a variety of different WebVR pages. These are all things that are live on the web right now through a variety of different sites. And you can see tracks what I'm looking at. In just a moment, you'll see that I can actually get up and walk around the room. We support room scale and a few other things like that. Forgive some of the choppiness of the video. I think that was the video capture rather than necessarily the actual display loop, because we do run, we can run at 90 hertz on the higher end VR hardware. And yeah, so where we're at today, as far as Chrome is concerned, we've actually made this available in Chrome Stable for Daydream devices, so the Google Pixel or other Daydream-capable devices. It's available as an origin trial, which what that means is that your site can actually opt into using this. It's not available by default everywhere, but your site can go out and get a token from us, opt into using it, and then anybody who visits your site will have that capability enabled by default. They don't have to go through about flags or anything like that to turn it on. It's available for Daydream right now. We're going to make it available for cardboard devices soon. And this is implementing what we kind of refer to as the WebVR 1.1 spec, which is not what we intend to be the final spec. And I can get into that in just a moment. On desktop, we've had some experimental builds out and available for a while that support the Vive and the Rift. You can get those at webvr.info if you want to play around with the API and you have higher end hardware. We are currently finalizing some of our plans for making that, getting those branches into top of tree. And there's just some security and legal issues that we're going through, making sure all licensing is kosher and whatnot. So we're getting there. Taking a little bit more time than I think most people would like, but we are getting there. As far as other browsers, there's implementations in one form or another available in Firefox Nightly. Oculus has put out what they call the Carmel browser. It's more of a WebVR viewer at this point than a proper browser, but I think that they're working towards making it a full-on browser. And then on GearVR, you can use the Samsung Internet browser, which has WebVR capabilities. That's a slightly older version of the API. We're still in a little bit of flux in terms of API support across the board. We're eventually going to settle that down. But you can experiment with these VR capabilities on the web on a variety of different platforms. And currently, we're working on what we're now referring to. We've called it by a couple of different names, kind of WebVR 2.0. Eventually, we just want it to be WebVR, like there's going to be a single feature that everybody accesses across the browser. And this is just working on reducing platform incompatibilities and edge cases that we've identified as we've been talking through supporting the spec on a variety of different platforms. We want to be able to use the API and workers. We want to support a wider variety of tracking needs. So we want to make sure that, for example, this works on anything from a cardboard to a HoloLens. And those have drastically different tracking needs, but we do feel like we can boil it down into a single, fairly sensible API. And we've also gotten a lot of feedback from the web platform leads in terms of how we can make the API fit better into the web as a whole, so it doesn't feel like kind of a weird outlier. So the moral of that being that we are breaking things right now. So if you go out and play with the API at the moment, you can make something that works, but you will need to eventually update it to keep it working in perpetuity. So after all of that, the question is, why am I on stage at a Khronos event? Because WebVR is not actually a Khronos API, at least not at this point. We actually haven't picked a standards body that we want to be under. It's currently a W3C community group, but we could go a variety of different ways for it, and we just haven't determined that that's the most important thing for us to do right now. Well, so the reason I'm up here is because WebVR actually gets along really, really well with Khronos standards, specifically WebGL. Now, at the moment, WebGL is the only way that you can actually push imagery to WebVR. That's probably not going to be the case long term. We do eventually want to bring in more of the DOM and more of, direct playback for videos and stuff like that to make developers' lives easier. But WebVR is where it's at right now, and the reason for that is like the path of least resistance for us. It's the easiest way for us to communicate here's what the headset capabilities are, render me a 3D scene. You can do that in WebGL very, very easily. Well, easily. If you use 3JS, it's easy. It gives us back information in pretty much the right format to push it almost directly out to the headset. I don't think it's an exaggeration to say that if we did not have WebGL available, WebVR would not be a thing. There's just way too much work that we would have had to put into the rest of the web platform to retrofit it onto VR, and we never would have gotten past the conceptual stage. But because WebGL was available, because that standard was available across all the different browsers, we could very easily say, yeah, we're going to just tell people to render in this and then plug in the results to the headset, and boom, we get a standard that's up and running fast. And it cannot be understated how much of an impact having WebGL as a standard available has impacted the development of WebVR. It's been awesome. And it's allowed us to use a very strong ecosystem that's built up around WebGL, such as 3JS, such as Babylon.js, such as any of the variety of different frameworks and libraries that have been built up around that. It's been a wonderfully good thing. In the future, we can look at things like OpenXR, which was announced just in the last couple of days. And WebVR is the type of application that really craves that kind of standard. Now, to be clear, WebVR doesn't have the same type of relationship with OpenXR or any of the VR APIs as WebGL and OpenGL ES. You can implement WebVR on top of pretty much any of the VR APIs. You can implement it on Windows Holographic. You can implement it on the Oculus SDK, the Daydream SDK, anything like that. And I expect that those will be implementations that stick around for a good long while going forward. Not everybody's going to use a single SDK or a single API to interface with. But if you have an API available like OpenXR, which supports a wide variety of hardware, that's really good for the browser vendors, because the browser vendors generally don't want to be kingmakers. We don't want to pick and choose which hardware we make use of. We don't want to build browsers that say you only work on NVIDIA hardware. Therefore, WebGL works on everything. We don't want to build browsers that say this only works with Oculus hardware. We want it to work everywhere, and OpenXR gives us an opportunity to do that. It gives us the ability to pick up new devices as they come onto the market instantly with no work on the browsers, on the browser's part. As long as we implement that standard, we gain access to everybody else. It makes it easier for us to implement. We have to do less backends. That means less maintenance. That means more focus on features and performance and all the good stuff that developers actually care about, rather than worrying about, well, do we support this one weird variant, of the headset from some no-name company that nobody's ever heard of, but that one guy on the bug list just really is insistent that we get it working. Open standards are a boon for things like WebVR, and we intend to make as much use of them as we possibly can. And it's worth mentioning that I've been working with the OpenXR group to make sure that the web's needs are well represented, and they've actually been enormously accepting to the idea that the web is an important use case, and applications like the web, things that just generally don't look like games, are an important use case for VR going forward. And so we've gotten a lot of support from that group in making sure that the API applies well to that. So this has actually been a pretty quick presentation, but I'll give some time back to the other presenters. One more video that I can end with. Well, in theory. Aw, is it not going to work? Let me try this one more time. Nope. I don't think we're going to actually work with that video, but that's okay. So in any case, thank you for your time, and now we'll hand it over to Neil to give an update on gLTF.
Okay, down to the last session, and we are going to have time for questions at the end, so get your tricky questions. You have a mic there, so mentally prepare yourself to walk up. So this is a session, myself and Saurabh from Microsoft, we're going to give you an update on gLTF. Just to remind folks, gLTF is a runtime 3D asset delivery format. It's yet another format, but it seems to be a format that's filling a gap in the ecosystem that wasn't being filled before. The other media types have their compressed, efficient standards. 3D didn't have one, and gLTF is filling that gap. And the thing that makes gLTF unique amongst the many different 3D formats that are out there, that it has all of these. It's compact, it's fast to load, it's definitely intended for runtime use, being transmitted across the network. It's not just meshes, it describes full scenes, animations, textures. It's runtime neutral. It assumes nothing about how you're going to use the assets. It just wants to get the assets to you to do whatever you want to do. And it's an extensible spec. And there's strong momentum in the industry. We have a good logo field here. Sketchfab is just the latest one. Oculus, Microsoft now using gLTF extensively. That's John Carmack saying, we need this, so it's all good. This is the kind of the reminder of the milestones that we're working to. We started work on this back in 2012, and the first use case was effectively and efficiently loading models into WebGL 1. And in December 2015, we released 1.0 spec, and that's been the spec version that's been driving this quite widespread adoption. At the third quarter last year, in 2016, we started doing a validator project, and that was an interesting exercise because it illustrated to ourselves that the spec could be polished. There are some corner cases that we could improve, and then we started getting strong requirements from the community in the industry saying that we want to become API independent. WebGL is awesome, but we want to start running gLTF assets easily on DX and Metal and other APIs as well. So we decided to move fairly aggressively to 2.0, which is where we're getting close to now. We have a pretty close to final 2.0 spec. We haven't finalized it yet. We wanted to use this opportunity to talk to this room full of people that hopefully care, that we have a month or two left to take feedback on the current 2.0 developer preview. Tell us what we've done wrong, and hopefully we've done some stuff right. But we have a window to fix it, so we're genuinely interested. Go to the GitHub and start filing comments and issues. We're going to be listening very carefully. And I should mention that just like WebGL, the gLTF is being done on GitHub. You can see the spec being created in real time. So we want, just like Ricardo was saying earlier, we want to encourage everyone to move to 2.0 as fast as possible. There are breaking changes from 1.0 to 2.0, but the new spec is easier to process. We've got rid of some of the road bumps, speed bumps in 1.0. And we were very nervous about doing a breaking change, but we had overwhelming community feedback that better to take the pain now. And it's not a significant amount of work to upgrade. So we're hoping, fingers crossed, that this is the right thing to do. And it seems so far the indicators are good. All the engines are quickly upgrading to 2.0. There we have the gLTF pipeline open source tool, which includes now a 1.0 to 2.0 translator that you can build into your workflow or use to translate models. And lots of the converters like Cloud to gLTF, OBJ to gLTF, they're all being upgraded as we speak to 2.0. The Khronos validator that started all of this is being upgraded, and other test suites, and a bunch of models and tutorials are coming too. So if you're working with gLTF, that's kind of the main message from this part of the presentation. Please consider moving to 2.0 as fast as you can. And as part of that, we always need more exporters out of tools. Primary export to gLTF without needing to translate is also obviously good. Blender has started work on a gLTF exporter, but we want to bring it up to 2.0. And so we've got some funding from Khronos to do a project to fund someone, perhaps in this room, to help us create a Blender 2.0 exporter, and the idea is that resultant code will be contributed back into the Blender open source code base. So we issued the RFQ yesterday. There's a link here. We just go to the RFQ page on Khronos. We want to get some bids, and we'll get going as fast as we can to get this done. And last but not least, before I hand over to Saurabh, just to kind of give you some insight into the kind of things we're thinking about for the roadmap. gLTF is quite modular, so it's easy to add different kinds of payloads into gLTF without breaking changes to the stuff that we have. A lot of interest in mesh compression. We're actually talking to the Draco team from Google, who are doing some awesome work, and that's very compatible with what gLTF can integrate. There's some progressive geometry streaming technology out of folks like Fraunhofer. You might have seen it in some of the SIGGRAPH demos, where you get a low res and it gradually refines itself. That might be useful for some use cases. The binomial guys out of Seattle have the basis format, which they're beginning to propose as an optimized single texture compressed format that can be very efficiently and easily expanded to any native GPU texture format once it hits the client. So we want an extension for more lighting control and perhaps some extensions for specific control of some of the underlying APIs if people want to get down into that kind of thing. So again, we're very interested in your feedback and priorities on what you'd like us to be doing with future versions. But next, let's get back and talk about what is in 2.0, and Saurabh from Microsoft is going to kind of walk you through it. Thanks.
Thanks, Neil. Just a quick update, quick 5-minute rundown on what's new in gLTF 2.0. By the way, I just noticed a little slide bug there. Neil's the gLTF chair. I'm just part of the working group. So what's new in gLTF 2.0? The main thing we really added is this concept of physically based rendering material definitions. These high-level material definitions allow you to really define a material using no API specifics, and you can then render the material on any lighting environment on any platform. I'll talk a little bit more about it a little later. The other part is gLTF 1 was really tied to WebGL. It required GLSL to be part of the asset, and a lot of engines were having trouble loading that GLSL shader code in there. You might be running on different devices, and you might not be able to support complex shader code. So by moving away from GLSL and defining this high-level material definition, we really want to go out there and be able to support this gLTF file format on any engine. If you really want to do GLSL, it's still possible. It's just now an extension as opposed to being part of the core spec. A couple of other improvements were we had this thing called a binary gLTF, which is a more compact binary representation, which was optional earlier, but now it's just part of the core spec. So we expect everyone to just implement that and get the benefits of that compact representation inside gLTF. And finally, we've made a few bug fixes that enhance kind of the JSON and JavaScript parsing performance in gLTF, which was really based on the community feedback we got from 1.0. So let's dig a little bit, not too much, into physically based rendering and what we are trying to do with the materials. So physically based rendering has been around for a while, and almost every game engine, almost every creation tool sort of does it already. But the challenge is no one does it exactly in the same way. Right? Everyone has their own intricacies. Everyone makes some assumptions on the math equations that go in there. And what gLTF gives you is really that standardization of when we say this is a metallic surface, what does that mean? And each exporter tool, like Blender, for example, or a rendering engine like 3JS or Babylon.js, knows exactly what that value means when we say a surface is metallic. And that's really what we're trying to do, is kind of standardize that across the board so that exporters can write something out into a gLTF file and renderers can read it in, and it means the exact same thing across engines, across exporters. This started off as a proposal from Fraunhofer. They proposed sort of an extension to the gLTF spec. It was quickly backed up. We loved the idea at Microsoft. So we went in and did some implementations in Babylon.js. And then Sketchfab has come along and has also had some implementations that show you this in action. And then other companies have also, once we've gotten the spec ready, adopted this core idea that we can have this standardized version of a PBR. So a little bit more into what we are supporting. There's two major workflows in physically based rendering. There's the metallic roughness workflow and specular glossiness workflow. If almost all engines support a particular variant of this, all we are doing here is just gathering all that data and saying, here's a standard way in which you can export out into these workflows. With the metallic roughness workflow, we made it part of the gLTF core because it's a little bit easier to implement it. So we expect each and every rendering device, rendering engine running on any device to be able to do a metallic roughness workflow. So even if you're on a low-power device, you should be able to implement metallic roughness and have the thing render. Specular glossiness requires a little more resources. We still want to support it, so we are going to do it as an extension. So if you want that finer grain control over your material models, you can still do specular glossiness, but you may not be able to support it across all the device instances because it's an extension and not all rendering engines might support it. You can combine both together and make it all part of one single gLTF file in which you kind of get best of both worlds. You get specular glossiness on devices that are capable of rendering it, and at the same time, if you're on a low-powered device, you can just drop back to metal roughness and render it on a low-powered device. So that's sort of the way we've proposed gLTF 2.0 spec, where both are supported. One's part of the core, and the other is an optional extension, which lets you use those additional resources if you have them. If not, just stick to the metal roughness in the core. Okay, so what does an actual gLTF file look like at a very high level? I talked about the JSON that gLTF has, and this has remained the same as in 1.0 in 2.0. The JSON is still there. We've changed the structure of the JSON a little bit. The JSON points out to these, almost think of them as like sidecar files, which contain the geometry, the binary data that makes up the wireframe of the model. The additional texture information or even the material information is embedded inside the textures, which really are just JPEG and PNG files, which you can also download. And then you kind of get all of that together and render a gLTF model. So with that, let me just switch over and just show you some examples of, gLTF working. So here's that same little boombox model. It's a gLTF model running in Babylon.js. This is a 2.0 model using the metallic roughness texture. You'll notice we are doing a little bit of image-based lighting here. So it's nighttime. It's nighttime here. I can switch it over to maybe take it outside, out in the country. The lighting changes. It's still the same model, but we've changed the lighting around it. And then I can even take it indoors with some real weird lighting, and it looks really different. So same model. I haven't changed the model at all. I've just changed the environment. I can relight it because it's now using these PBR material definitions. Now, this is common. A lot of people have, Babylon.js does it, 3JS does it in the engine. But what really makes gLTF different is you can now do it across engines and across platforms. Right, so this is the same model. Down there is a 3JS example, exact same model, 2.0 model, but in a different environment. On the right there is, again, the same model, but running on Vulkan, right? So not even a WebGL API. And that's really the true kind of ubiquity of gLTF, where we are going API neutral. We want to define these common models that you can just pick up, load them in your engine, whatever API you're running on, and render them. So that was a quick rundown of 2.0. The call to action, we have a draft spec. It's on the GitHub repo. We also have all these sample models, the Boombox model and many more, which allow you to play around with the concept of PBR. We actually are getting a lot of feedback that people are using these models to learn about PBR and sort of implement PBR in their engines, which is really great. So you can go on GitHub, start commenting on the spec, start implementing a gLTF 2.0 and PBR in your engine. And then again, shout out to if you're interested in the Blender RFQ, that's also up there on GitHub. So with that, I hope to see you all on GitHub. Thank you.
All right, awesome, Saurabh, thank you. Saurabh is spec editor, by the way, just so you know. So we have time for questions. So we have everyone here. So feel free to ask a couple questions. We have like 5 minutes. I know, but it's okay. We have 5 minutes. So any questions whilst we're waiting? There we do have a meetup session, which is open to everyone. It's on Thursday evening, 6:30. The details are on this little red card, so grab one of these if you're able. All right, looks like everyone's going. Okay, bye.
Thanks, Neil. So yeah, if you have any questions, we'll be here for a little bit. You can just come up and talk to us. There's lots of good stuff that we would love to talk to you about.